A meta-analysis of 33 studies involving more than 102,000 men and women found that each single unit increase in cardiorespiratory fitness, measured in metabolic equivalents, was associated with a 13% reduction in all-cause mortality and a 15% reduction in cardiovascular events. To put that in practical terms, the least fit adults in these studies had approximately double the mortality risk of the most fit adults. Not double the risk compared to elite athletes, double the risk compared to people who were simply not in the bottom quintile of fitness. For anyone over 55, this number demands attention. Let that comparison sit for a moment. The gap this study is describing is not between a sedentary adult and a marathon runner. It is between a sedentary adult and someone who walks briskly, takes the stairs, and can sustain moderate aerobic effort for 15 minutes without stopping. The mortality difference between those two people, averaged across 102,000 participants in 33 studies, is a factor of 2. That is a larger risk reduction than most pharmacological cardiovascular interventions available today. And unlike medications, it has no copay, no pharmacist, and no prescription required, only a plan, a pair of shoes, and the understanding that the evidence supports it. This finding positions VO2max not as an athletic metric but as a clinical vital sign, one that predicts not just performance in the gym but probability of surviving the next decade. The cardiologist Peter Attia has described cardiorespiratory fitness as the most powerful variable he tracks in his patients, and the Kodama meta-analysis is the foundational reference behind that clinical judgment. For adults in their mid-50s who are still in the phase of life where intervention can meaningfully reshape their trajectory, this data is among the most important in the longevity literature. In this video, we will cover what VO2max actually is and why it matters far beyond athletic performance, why it declines with age and what that decline means concretely for daily function and longevity risk, what the Kodama meta-analysis found across more than 100,000 participants, how to estimate your own cardiorespiratory fitness without setting foot in a laboratory, and 3 practical steps for improving or preserving VO2max that are grounded in what the evidence actually supports for this age group. Quick note before we begin, this is educational content based on published research, not medical advice. Talk to your physician before changing your regimen. Now, the study. VO2max is the maximum rate at which the body can consume oxygen during sustained exercise, the integrated sealing of the heart, lungs, blood vessels, and working muscles. It is expressed in milliliters of oxygen per kilogram of body weight per minute. The clinically meaningful comparison is not between average and elite, it is between the bottom quintile of fitness and the rest of the population. The challenge for adults over 55 is well documented. VO2max declines at approximately 10% per decade after the age of 30, even in people who remain active. The mechanisms include reduced maximal cardiac output, decreased arterial compliance, lower mitochondrial density in skeletal muscle, and a lower maximum heart rate. By 65, a sedentary person may have lost 30 to 40% of the cardiorespiratory capacity they had at 30. The practical consequences are visible: the breathlessness climbing stairs that did not exist at 45, the difficulty sustaining a conversation while walking uphill, the longer recovery after exertion. But here is what makes this story important rather than merely discouraging: VO2max is trainable at any age. Cardiorespiratory fitness responds to aerobic training with meaningful improvements even in adults in their 70s and 80s, gains that can move a person from the bottom quintile into the second or third quintile, representing a dramatic shift in mortality risk according to the Kodama data. The 2009 Kodama meta-analysis was designed specifically to aggregate the evidence and produce the most reliable quantitative estimate of the longevity benefit per unit of fitness improvement. A study published in JAMA by Kodama and colleagues conducted a systematic meta-analysis of 33 prospective cohort studies involving 102,980 participants. The goal was to produce a pooled quantitative estimate of how cardiorespiratory fitness, measured as either directly assessed VO2max via metabolic cart testing or exercise test performance expressed in metabolic equivalents, predicted all-cause mortality and cardiovascular events. This kind of systematic aggregation is valuable precisely because it transcends the limitations of any individual study, pooling large amounts of data across diverse populations in study designs to arrive at the most reliable estimate available. Metabolic equivalents, or METs, are a standardized unit of exercise intensity relative to resting metabolic rate. 1 MET equals the energy cost of sitting quietly. Walking briskly is roughly 3 to 4 METs. A jogging pace is 6 to 7 METs. Running at 7 minutes per mile is approximately 11 METs. Importantly, 1 met of increase in assessed cardiorespiratory fitness, the unit the Kodama analysis uses to express its findings, represents a meaningful but achievable improvement over months of consistent moderate aerobic training. It is not a one-workout change. It reflects the cumulative physiological adaptation to sustained training over weeks to months. The populations in the included studies were primarily healthy adults without known disease at baseline, which makes this analysis directly relevant to people in their 50s and 60s who are managing long-term risk rather than recovering from an acute illness. Studies were excluded if they did not report fitness using standardized exercise testing, ensuring the findings could be expressed in comparable units across the entire pooled dataset. This methodological gate kept the analysis from being diluted by studies using unreliable fitness proxies. The analysis adjusted for age, sex, body mass index, smoking status, and other conventional cardiovascular risk factors. This adjustment is critical to the interpretation. The fitness effect observed was not simply explained by the fact that fit people tend also to be non-smokers with healthy body weights who eat better diets. Even after statistically accounting for those correlated variables, cardiorespiratory fitness retains substantial and independent predictive power for mortality and cardiovascular event rates. That independent effect, the portion of mortality risk variation attributable to fitness itself, above and beyond all the correlated health behaviors, was the number the Kodama team was most interested in quantifying. What the researchers found was a clear, dose-response gradient, more fitness, consistently less mortality risk, across the full distribution of the fitness spectrum. The relationship was not confined to the comparison between elite athletes and average people. It was present continuously across the entire fitness range, with the steepest risk reduction, the largest mortality benefit per unit of improvement occurring as people moved from the lowest fitness quintile upward into the second and third quintiles. This gradient shape is important, because it means the highest impact population for intervention is not athletes chasing marginal gains. It is the large number of adults in their 50s and 60s who are currently in the lowest fitness category. The researchers reported that each 1 met increase in cardiorespiratory fitness was associated with a 13% reduction in all-cause mortality. For cardiovascular events specifically, each 1 met increase corresponded to a 15% reduction in risk. These are per unit effects, and they are additive within the range of the fitness distribution studied. A person who improves their cardiorespiratory fitness by 2 mets through consistent aerobic training, a realistic outcome over 4 to 6 months, could, according to this model, be looking at approximately a 26% reduction in all-cause mortality risk. A 2 met improvement is not hypothetical. It is the documented outcome of moderate intensity aerobic training programs studied in adults in their 60s and 70s. The quintile comparison was equally striking. Adults in the lowest quintile of cardiorespiratory fitness had approximately double the all-cause mortality risk of those in the highest quintile. When the analysis was restricted to cardiovascular mortality specifically, the risk differential between the lowest and highest fitness groups was even larger. This is a remarkable finding when stated plainly. Being in the bottom 20% of cardiorespiratory fitness, compared to being in the top 20%, roughly doubles your risk of dying during the follow-up period, independent of other measured risk factors. What the researchers found next is even more important for this age group. The effect was consistent across sex. Men and women showed similar magnitudes of risk reduction per unit of fitness improvement. This matters because earlier research had sometimes suggested the mortality-fitness relationship might be weaker or less consistent in women, particularly older women. The Kodama pooled analysis, with over 100,000 participants, did not support that conclusion. The association was robust in both sexes. The fitness-mortality relationship also remained robust after excluding studies with follow-up periods of less than 5 years, a sensitivity analysis designed to address reverse causation. The concern is that people with serious underlying illness have both lower fitness and higher mortality, making it appear as if low fitness causes higher mortality when in fact illness causes both. By removing short follow-up studies, where reverse causation is most likely, and finding that the association persisted, the researchers provided meaningful reassurance that the relationship is not primarily an artifact of this bias. One additional finding worth noting: there appeared to be no plateau in the protective effect within the range of fitness levels observed across the community populations in these studies. More fitness continued to predict lower mortality risk even at higher fitness levels, though the incremental benefit per unit of improvement was smaller at higher absolute fitness than at the low to moderate transition zone where the most dramatic risk reductions were observed. The limitations of this study deserve attention before we act on it. Meta-analyses pool observational cohort data, and even prospective observational data carries inherent limitations. While fitness was measured before outcomes occurred, which prevents the worst forms of reverse causation, the studies are still observational. We cannot fully rule out residual confounding. Healthy, motivated adults who maintain high cardiorespiratory fitness throughout middle age may differ from low-fitness adults in dozens of behavioral, genetic, and socioeconomic ways that are difficult to fully measure and adjust for in even the most comprehensive statistical model. The association between fitness and longevity is robust, but calling it definitively causal requires caution. The measurement of fitness also varied across included studies. Some used direct VO2max testing with metabolic carts, the gold standard, which requires laboratory equipment and maximal effort protocols. Others used submaximal exercise tests and estimated VO2max from heart rate response at submaximal workloads, a less precise method that introduces measurement error. The conversion of these heterogeneous measurements into a common MET-based unit requires assumptions that may not hold perfectly across all study contexts. There is also a genuine philosophical question in fitness research: does the association reflect a causal relationship between fitness and longevity, or does it reflect VO2max as a marker of underlying biological health? It is possible that the same genetic and physiological factors that enable high cardiorespiratory capacity are what independently drive longevity, meaning fitness is measuring underlying health rather than causing it. This distinction has practical implications, because if fitness is a cause, training it changes outcomes; if it is only a marker, training it might not produce the same mortality benefit as naturally high fitness. The pragmatic answer is that the distinction may matter less than it appears. Because VO2max is demonstrably trainable, and because aerobic training produces concrete, measurable biological adaptations, including reduced arterial stiffness, improved insulin sensitivity, lower resting heart rate, reduced inflammatory markers, and enhanced cardiac output, the biological plausibility of the causal story is strong. The research on this point has grown substantially since the Kodama analysis, with multiple prospective training intervention studies in older adults confirming that the adaptations associated with high fitness are real, not merely markers of pre-existing health. 3 takeaways from this research for anyone in the 55-plus window who wants to use this evidence practically. Takeaway 1: establish your current cardiorespiratory fitness baseline even without a laboratory. The 6-minute walk test is a validated, low-technology method widely used in clinical research with older adults. Walk as far as you can in 6 minutes on a flat, measured surface, then compare your distance to age and sex-specific normative tables available in published clinical references. A 60-year-old woman covering fewer than 480 meters in 6 minutes, or a 60-year-old man covering fewer than 520 meters, is in a fitness range associated with significantly elevated risk in the literature. The specific thresholds differ by age and sex, and your physician can help interpret the result. The point is not to achieve a specific number on the first test, it is to establish a baseline that can be tracked over months and years. What gets measured gets managed. If your physician determines this is appropriate for you, asking about formal cardiopulmonary exercise testing, a clinical treadmill or cycle ergometer test that directly measures VO2max, provides the most precise MET value and can be repeated to track the impact of training over time. Takeaway 2: understand where the greatest mortality gains are located in the fitness distribution. The Kodama data shows that moving from the bottom quintile of cardiorespiratory fitness to the second quintile carries a larger mortality risk reduction than moving from the third quintile to the fourth. This is where the arithmetic of this research is most important. The people who stand to gain most are not athletes pursuing marginal optimization. They are sedentary adults in their late 50s and early 60s who are currently doing little to no sustained aerobic activity. For that group, starting with 20 to 30 minutes of brisk walking 3 to 4 times a week and building from there is not minor medicine. According to the Kodama meta-analysis, it is among the most consequential risk reduction interventions available, more impactful per unit of effort than many pharmaceuticals studied in the same population. Takeaway 3: VO2max decline is not biologically predetermined in its magnitude, it is largely driven by inactivity. The 10% per decade decline measured in population studies reflects a sedentary population norm, not an immutable ceiling. Published data from masters athletes in their 60s and 70s show measured VO2 max values that exceed those of sedentary adults 30 years younger. The mechanism for slowing decline is consistent moderate to vigorous aerobic training. The Zone 2 work discussed in earlier videos on this channel forms the aerobic base, while periodic higher intensity interval sessions provide the cardiovascular stimulus for adaptation at the upper end of the heart rate range. 3 to 4 sessions per week of sustained aerobic effort, progressively accumulated over months and years, is associated with meaningful preservation of cardiorespiratory fitness well into the 7th and 8th decade of life. Discuss with your physician what intensity level and testing protocol is appropriate for your specific cardiovascular and musculoskeletal profile before significantly increasing aerobic training load. The Kodama meta-analysis of over 100,000 adults makes the case clearly and quantitatively. Cardiorespiratory fitness is among the most powerful predictors of how long someone lives and how well they age, and it responds to training at any age. A 13% all-cause mortality reduction per MET of improvement, compounding with each additional MET gained through consistent training, is not a marginal statistical signal. It is a clinically meaningful effect that rivals or exceeds most pharmaceutical cardiovascular interventions studied in this age group. And unlike medications, it generates additional benefits across metabolic, cognitive, and musculoskeletal health simultaneously. For adults in their mid-50s who still have 15 to 20 years of active life ahead of them, the decision about whether to invest in building and maintaining cardiorespiratory fitness is one of the highest return health decisions available. Download the PDF guide on reading your biomarker panel, link in the description, which includes the fitness metrics and cardiovascular markers worth tracking alongside your standard blood work. Subscribe for the next video, where we continue building the evidence-based picture of longevity for this age group. This is educational content, not medical advice. Always consult with your physician before changing your regimen. Studies are preliminary, individual responses vary.